Good morning everyone. This is Triveni MK working as an assistant professor in the Department of Chemistry, Maharaja Institute of Technology, Mysuru. In this session, we discuss about derivation of Nernst equation for EMF of a galvanic cell and problems on Nernst equation. Before the derivation, let us recall the definition for electrode potential and standard electrode potential. The potential that is developed when an element, it may be a metal or a non-metal, which is in equilibrium with its own ions in solution, is called electrode potential, and it is denoted by the letter E. E represents the electrode potential. The potential that is developed when an element is in equilibrium with a solution of its own ions of unit concentration. So that is 1 molar at 298 Kelvin, and if the electrode system involves the gaseous substances, they must be passed at a pressure of 1 atmosphere at 298 Kelvin is known as standard electrode potential, and it is denoted as E naught. So observe that E represent the electrode potential at any temperature and E naught represent the standard electrode potential at 298 Kelvin. If the electrode system involves the gaseous substances, they must be passed at a pressure of 1 atmosphere. If the electrode system involves a solution, the concentration of solution is 1 molar at 298 Kelvin is considered as standard electrode potential. The standard electrode potential of all electrodes are measured with respect to She. She means standard hydrogen electrode. If the conditions like temperature or concentration of the metal ions, or changes, the electrode potential changes. So therefore, it is very difficult to measure the electrode potential every time experimentally when the conditions are changed. So therefore, in 1889, Nernst derived a quantitative relationship between electrode potential and concentration of metal ions. This expression is considered as a Nernst equation. This equation have great help in calculating the electrode potential of any electrodes when the conditions are changed without conducting the experiment. This is the application of Nernst equation. Let us discuss the derivation of Nernst equation. The Nernst equation is derived with the help of thermodynamic concept. To derive this equation, first let us consider a reversible electrode reaction. Like Mn plus N electrons giving M. Observe this equation. To derive the Nernst equation, first we have to consider a reversible electrode reaction of the type Mn plus N electron giving metal. So by the convention, electrode reaction is written with reduction in the forward direction as electrode potential. Observe that the forward reaction represents the reduction reaction, because by convention potential is generally expressed in terms of reduction potential. So therefore always we have to write the forward reaction as a reduction reaction. For this equation, observe that this is a equilibrium reaction. So write the equilibrium constant. Equilibrium constant is represented by Kc. For the above reaction is, observe that for any reversible reaction, equilibrium constant is nothing but it is the ratio of molar concentration of products to molar concentration of reactants. So observe that here the product is metal and the reactant is metal ion. So therefore the expression becomes M molar concentration of metal divided by molar concentration of metal ion. This square bracket represents the molar concentration of the species. So second step, write the equilibrium constant expression for this equation. So therefore the equilibrium constant Kc for this equation is equal to molar concentration of metal by molar concentration of metal ion. Let us call this equation 1. According to the thermodynamics, the equilibrium constant Kc is related with change in free energy as delta G is equal to delta G naught plus RT natural log Kc. Observe that according to thermodynamics, equilibrium constant Kc is related with change in free energy as delta G is equal to delta G naught plus RT natural log Kc. Let us call this equation 2. In this equation, delta represent the small change, G represent the free energy. So, therefore, delta G is change in free energy. Delta G naught represent the standard free energy change for the same process. R is a gas constant and T is the temperature in Kelvin scale and Kc represent the equilibrium constant. For any reversible reaction, the decrease in free energy change is equal to maximum amount of work done by the system. For any reversible process, always the decrease in free energy is equal to the maximum amount of work done by the system. So, it is represented like this. This negative sign represents the decrease in free energy change and W max represent the maximum amount of work done by the system. In case of galvanic cell, maximum work done is equal to electrical energy supplied by the cell. So, for a galvanic cell, the maximum work done is equal to the electrical energy supplied by the cell. Then how to calculate the electrical energy supplied by the cell? Recall the previous session, that is the construction and working of galvanic cell. The electrical energy supplied by the cell is nothing but the difference in potential between the two electrodes and the total quantity of charges flowing through the cell. So, electrical energy supplied by the cell is nothing but it is difference in potential between two electrodes into total quantity of charges flowing through the cell. So, the electrical energy supplied by the cell is nothing but it is the combination of difference in potential between two electrodes into total quantity of charges flowing through the cell. The difference in electrode potential is nothing but it is the potential of the cell, it is denoted by E cell. The difference in potential between two electrodes is nothing but it is the potential of the cell or it is denoted by E cell. If recall that if n moles of electrons are flowing from anode to cathode, then the total quantity of charges flowing through the cell is n Faradays. So, therefore, the total number of charges flowing through the cell is n, that is the number of electrons flowing from anode to cathode into Faradays. So, this is maximum work is equal to difference between the two electrode, that is E cell, into NF. So, simplify this as NFE. So, therefore, minus delta G is equal to NFE. Call this equation 3. Observe that maximum amount of work is equal to minus delta G. So, hence delta G is equal to NFE. So, under standard conditions, the above equation is reduced to minus delta G naught equals NF E naught. Call this equation 4. Under standard conditions, the change in free energy measured becomes delta G naught and the electrode potential measured becomes standard electrode potential. So therefore expression is reduced to minus delta G naught is equal to NF E naught. So substitute the equation 1, 3 and 4 in equation 2. Substituting the values of equation 1, equation 3 and equation 4 in equation 2. Substituting equation 1, 3 and 4 in equation 2. Minus N F E is equal to minus N F E naught plus RT natural log concentration of metal divided by concentration of metal ion. Substitute the values of equation 1, that is Kc expression, to this, and 3 means delta G is equal to NFE and delta G naught. Okay. So we get this equation. Divide this equation throughout by minus NF. Divide this equation throughout by minus NF. We get E is equal to E naught. Observe that plus into minus become minus RT divided by NF natural log concentration of metal divided by concentration of metal ion. Okay. So observe that this equation, I will alter this equation like this. E is equal to E naught. Instead of minus, I will write this one as a positive. Therefore, what happens? This ratio is interchange. RT divided by NF natural log concentration of metal ion divided by concentration of metal. For in thermodynamics, the concentration of solid is always taken as unity. So in this case, we are considering a metal ion electrode. So therefore, concentration of metal is equal to 1. So substitute this value in this equation, then we get the equation like this. E is equal to RT divided by NF natural log concentration of metal ion. This equation is known as basic Nernst equation. This equation is known as basic Nernst equation. Next, change the natural log to log base 10. Change the natural log to log base 10. What is the conversion factor? We have to multiply this by 2.303. So therefore, we get E is equal to E naught plus RT divided by 2.303 RT divided by NF log base 10 of concentration of metal ion. This equation is known as a Nernst equation for single electrode potential at any temperature. Observe that we have to change the natural log to log base 10. So we have to add the conversion factor, that is 2.303. So therefore, above equation is reduced to E is equal to E naught plus 2.303 RT divided by NF log base 10 of concentration of metal ion. This equation is known as a Nernst equation for single electrode potential at any temperature. Substitute the values of R. What is R? R is a gas constant. Its value is 8.314 joule per Kelvin per mole. Then T is 298 Kelvin and F is Faraday's constant. Its value is 96,500 joule per volt per mole. Substitute the values of R, T and F and simplify. We get the equation like this. E is equal to E naught plus 0.0591 divided by n log base 10 of concentration of metal ion. This equation, observe that E is equal to E naught plus 0.0591 divided by n log base 10 of concentration of metal ion. This equation is known as Nernst equation for single electrode potential at 298 Kelvin. So, this is the derivation of Nernst equation. Nernst equation is derived with the help of thermodynamic concept. Let us once again revise the derivation of Nernst equation. To derive the Nernst equation, first we have to consider a reversible electrode reaction, that is Mn plus n electrons giving metal. Write the equilibrium constant for the above equation. The equilibrium constant expression for this equation is Kc is equal to molar concentration of metal divided by molar concentration of metal ion. Let us consider this equation 1. For any reversible reaction, according to thermodynamic, equilibrium constant Kc is related with change in free energy as delta G is equal to delta G naught plus RT natural log Kc. For any reversible process, the decrease in free energy, always the change in free energy decreases for a reversible reaction. So, therefore, decrease in free energy change is equal to maximum amount of work done by the system. We are deriving the Nernst equation for galvanic cell. So, therefore, in case of galvanic cell, maximum amount of work done is equal to electrical energy supplied by the cell. The electrical energy supplied by the cell is nothing but it is the difference in potential between two electrodes into total quantity of charges flowing through the cell. The difference in potential between two electrodes is nothing but it is the EMF of the cell or E cell, and if n moles of electrons are flowing from anode to cathode through the external circuit, the total number of charges flowing through the cell is n Faradays. So, simplify this as NFE. So, therefore, observe that maximum amount of work done is equal to decrease in free energy change, hence decrease in free energy change is equal to NFE. Call this equation 3. Under standard conditions, so minus delta G naught is equal to NFE naught. So, substituting the equation 1, 3 and equation 4 in equation 2, we get this expression, that is minus NFE is equal to minus NFE naught plus RT natural log of concentration of metal divided by concentration of metal ion. Divide this equation throughout by minus NF. Then this equation is reduced to E is equal to E naught minus RT divided by NF natural log of concentration of metal divided by concentration of metal ion. Or I am changing this equation, so therefore numerator and denominator will interchange. So, therefore, we get this expression. So, for solid concentration always considered as unity. So, here this electrode is a metal ion electrode. So, therefore, the concentration of metal becomes solid. So, therefore, its concentration is 1. So, therefore, we get this expression, that is E is equal to E naught plus RT divided by NF natural log of concentration of metal ion. This expression is known as a basic Nernst equation for single electrode potential. So, change the natural log to log base 10. So, then this equation is reduced to E is equal to E naught plus 2.303 RT divided by NF log base 10 of concentration of metal ion. Then substitute the values of R, T and F. So, R value is 8.314, unit is important, joule per Kelvin per mole, and T is 298 Kelvin, and F is a Faraday constant, its value is 96,500 joule per mole. Substitute all these values to this equation and simplify that, then we get this equation E is equal to E naught plus 0.0591 divided by N log base 10 of concentration of metal ion. This equation is known as Nernst equation for single electrode potential or half cell potential at 298 Kelvin. It is also considered as a Nernst equation for electrode potential at 298 Kelvin. Now, let us derive the Nernst equation for EMF of a galvanic cell. We know that EMF of a galvanic cell is given by E cell is equal to electrode potential of cathode minus electrode potential of anode. This is the equation to calculate the electrode potential of galvanic cell. We know that EMF of a galvanic cell is given by E cell is equal to electrode potential of cathode minus electrode potential of anode. So, substituting the Nernst equation for single electrode potential separately for anode and cathode, then the equation, then the expression for the E cell is, so we have to substituting the Nernst equation for single electrode potential separately for anode and cathode. Recall the Nernst equation for single electrode potential. E cathode is nothing but it is E naught of cathode plus 2.303 RT divided by NF log base 10 of concentration of metal ion at cathode. Concentration of metal ion at cathode minus, so then we have to substitute the single Nernst expression for single electrode potential for anode. So, that is E naught anode, standard electrode potential for anode plus 2.303 RT divided by NF log base 10 of concentration of metal ion at anode. Observe that to derive the Nernst equation for EMF of a galvanic cell, so substituting the Nernst equation for single electrode potential separately for anode and cathode. So, therefore, E cell is equal to E naught of cathode plus 2.303 RT divided by NF log base 10 of concentration of metal ion at cathode minus standard electrode potential of anode plus 2.303 RT divided by NF log base 10 of concentration of metal ion at anode. Next, simplify this equation and taking out common factor. So, that is E naught cathode minus E naught anode, taking out the common factor, plus 2.303 RT divided by NF log base 10 of, observe that this is log A minus log B form. So, log A minus log B can be written as log A by B. So, therefore, this become Mn plus at cathode divided by concentration of ion at anode. So, observe that simplifying this equation and taking out the common factors, E naught cathode minus E naught anode plus 2.303 RT divided by NF is common in both the expression, taking out this 2.303 RT divided by NF log base 10. So, then this is log A minus log B. We can write this as log A by B. So, therefore, log concentration of metal ion at cathode by concentration of metal ion at anode. So, observe that E naught cathode minus E naught anode. So, observe this equation, E cell is equal to electrode potential of cathode minus electrode potential of anode. Here, observe this expression, standard electrode potential of cathode minus standard electrode potential of anode. So, therefore, this we can write this like this, that is E naught cell. So, therefore, E cell is equal to E naught cell plus 2.303 RT divided by NF log base 10 of concentration of metal ion at cathode divided by concentration of metal ion at anode. This is the Nernst equation for EMF of a galvanic cell at any temperature. So, this equation is used to calculate the EMF of a galvanic cell at any temperature. Next, substituting the values of R, T and F. What is the R value? R value is 8.314 joule per Kelvin per mole. Temperature is 298 Kelvin and Faraday, F is Faraday constant, its value is 96,500 joule per volt per mole. Substitute the values and simplify that, then this equation is reduced to E cell is equal to E naught cell plus 0.0591 divided by N log base 10 of concentration of metal ion at cathode divided by concentration of metal ion at anode. This equation is known as a Nernst equation for EMF of a galvanic cell at 298 Kelvin. This equation is considered as a EMF of a galvanic cell at 298 Kelvin. So, what is the R value? R value is 8.314 joule per Kelvin per mole. So, what is T value? 298 Kelvin, it is the standard temperature. Next, F value is 96,500 joule per volt per mole. So, observe that electrode potential is generally represented by volts. Simplify the units. Observe that. So, R value is joule per Kelvin per mole, T is temperature, F value is 96,500 coulomb, joule get cancelled, mole get cancelled, then per volt becomes volt. So, therefore, last answer we have to express the EMF of a cell in volt. So, therefore, the unit is volt. Is it clear? So, derivation of Nernst equation for EMF of a galvanic cell. Now, let us discuss the problems on Nernst equation. So, first problem, calculate the EMF of a Daniell cell at 298 Kelvin. If the free energy change of the cell reaction is minus 212.3 kilojoule per mole. F is a Faraday constant is equal to 96.500 kilojoule per mole per volt. So, observe this problem. So, first we have to write down the given data in the problem. So, read the problem once again. Calculate the EMF of a Daniell cell. EMF of a Daniell cell means we have to calculate the electrode potential, that is E. Temperature given is 298 Kelvin and the free energy change is given. Free energy means it is delta G value is given. Its value is minus 212.3 kilojoule per mole. Next, F value is given. F value is 96.5 kilojoule per mole per volt. So, according to the given data, so write down the formula to calculate the problem. The formula for this experiment is, it is minus delta G, the decrease in free energy is equal to NFE. So, using this equation, we can easily calculate the electrode potential of the given cell. So, reduce this equation in terms of E. So, therefore, this equation becomes E is equal to minus delta G divided by NF, where N represent the number of electrons involved in the redox reaction. Observe that in the problem they are mentioning the Daniell cell. Daniell cell means zinc rod dipped in zinc sulfate and copper rod dipped in copper sulfate solution. That means the N value is 2 in this case. Next, substitute the values according to the given data. Delta G value is minus, so minus 212.3 divided by N value is 2. Next, F value is 96.5. So, simplify this equation, minus into minus become plus. So, therefore, the answer become 1.1 volt. So, observe that delta G value is given, its value is minus 212.3. then N value according to Daniell cell means N value is 2, then F value is 96.5 kilojoule per mole per volt. Substitute the values and simplify that, then we get the value as 1.1 volt. So let us come to the next problem. Next problem, calculate the electrode of reduction of copper electrode when the free energy change for the reaction. So this reaction represents the reduction reaction of the copper, that is cupric ions gains 2 electrons from the anode compartment, then it is reduced to copper. So during this reaction, so the electrode potential, the free energy change is minus 62.755 kilojoule per mole. So according to this, the solution for this problem is given is, they are mentioning the delta G value. Delta G is minus 62.755 kilojoule per mole. They are not mentioning the F value. F is a Faraday constant. It is always remains constant. Its value is 96,500. Observe that here they are mentioning the delta G value in terms of kilojoules. So therefore we have to write the F value in terms of kilojoule. So therefore it becomes 96.5 kilojoule, 96,500. So convert that into kilojoule means it becomes 96.5 kilojoule. Observe that the F value is written here, that is kilojoule per mole per volt. Next we have to calculate the EMF of the cell, that is E. So therefore once again the formula is minus delta G is equal to NFE. Substitute the values, reduce this equation in terms of E. So therefore minus delta G divided by NF. Delta G value is minus of 60 to 62.755 divided by N value is 2. Observe that this gives the N value, number of electrons involved in the reaction is 2. So therefore N value is 2 and F value is 96.5. So simplify this equation, we get 0.325 volt. This is the first type problem. In the next problem, this is a second type problem. Calculate the reduction potential of zinc for the equation. Equation is reduction of zinc, that is Zn2 plus ions, zinc ions gains 2 electron, then it is reduced to zinc. They are mentioning the standard electrode potential of zinc, its value is minus 0.76 volt and the concentration of zinc ion is given. So observe this problem. In this problem they are mentioning the value of standard reduction potential of zinc and the metal ion concentration is given. So therefore we have to use the Nernst equation for single electrode potential. So what is that expression? The expression is E is equal to E naught plus, observe that they are not mentioning the temperature. So if they are not mentioning the temperature means the reaction we have to consider the standard temperature, that is 298 Kelvin. So therefore we have to use the equation E is equal to E naught plus 0.0591 divided by N log base 10 of concentration of metal ion. Observe that E naught value is given and the metal ion concentration is mentioned. So therefore we can easily calculate the EMF of the cell. Next substitute the values. E naught value according to the given problem, it is minus 0.76 volt plus 0.0591. So observe the equation. N represent the number of electrons involved in the reduction reaction, its value is 2, then log base 10 of metal ion concentration, here the metal is a zinc, zinc ion concentration is 0.1 molar. So next observe that equation, Nernst equation for single electrode potential general expression is E is equal to E naught plus 0.0591 divided by N log base 10 of concentration of metal ion. Here, so E represent the electrode potential of zinc and E naught represent the standard reduction potential of zinc and Mn represent the zinc ion concentration. Next, on substituting the value of standard electrode potential of zinc, according to the problem it is minus 0.76 volt plus 0.0591 divided by the number of electrons involved in the reduction is 2. So, therefore, it becomes 2, then log base 10 of 0.1. Simplify this equation, minus 0.76 plus 0.0591 divided by 2 means 0.0295. So, log 0.1 is nothing but, observe that, so 0.1 can be written as 1 divided by 10. So, this can be written as 10 to the power minus 1. So, observe that this is in the form of log a to the power m. It can be written as m log a. So, therefore, minus 1 log 10, log 10 value is 1. So, therefore, minus 1 into 1 means this its value become minus 1 into minus 1. So, therefore, minus 0.76 plus into minus become minus 0.0295. So, therefore, answer is minus 0.7895 volt. This is the electrode potential for the given problem. Is it clear? Observe that in this problem they are mentioning the metal ion concentration and the standard electrode potential. So, therefore, we have to use this equation, then substitute the values and simplify that, then we get the answer as minus 0.7895 volt. Next, come to the next problem. In this problem, calculate the standard reduction potential of copper when the reduction potential of copper is, they are mentioning the reduction potential of copper, but they are asked to calculate the standard reduction potential of copper and they are mentioning the concentration of cupric ions. So, therefore, we have to use the same equation, that is E is equal to E naught plus 0.0591 divided by N log base 10 of concentration of metal ion. So, I am reducing this expression in terms of copper. So, therefore, it become ECu2 plus Cu. This represents the reduction potential of copper. Then standard reduction potential of copper plus 0.0591 divided by N log base 10 of concentration of cupric ions. Observe that we have to find out this value. So, therefore, I am reducing this equation in terms of E naught value. So, therefore, this equation is reduced to E naught Cu2 plus bar Cu is equal to electrode potential of copper minus 0.0591 divided by N log base 10 of concentration of cupric ions is 0.015. Substitute the value 0.296 minus 0.0591 divided to log base 10 of 0.015. Simplify this. On simplification, we got 0.3494 volt. So, this is the standard reduction potential of copper as 0.3494 volt. Is it clear? So, observe that here, so they are asking to find out the standard reduction potential of copper. They are mentioning the electrode potential of copper and the concentration of metal ion. So, therefore, to solve this problem, we have to reduce this equation in terms of standard reduction potential of copper. So, therefore, this equation is reduced to E naught of copper is equal to E of copper minus 0.0591 divided by N log base 10 of concentration of cupric ions. Then simplify this, we get the answer as 0.3494 volt.